So now that we have an idea of what indifference curves are, let's talk about 4 different properties of indifference curves. So 4 properties of indifference curves. Long title, I guess. All right, so the first property is going to be that they're downward sloping. We have downward sloping indifference curves. And why we know this is going to be true is that if we drew out our indifference curves like we just did with mangoes and fish for Alex, remember that indifference curves show the different combinations of goods that give them the same total utility. So the different bundles or different consumption bundles that give Alex the same total utility, or that he would be indifferent towards consuming. So be indifferent towards consuming these different combinations of goods because they give him the same total utility. And so we had 2 points before, point A and point B. And so both of these points give different consumption bundles. So this was, the quantity of fish. I think this is the nomenclature, the subscripts I used. So the number of the quantity of fish at point A, and this is the quantity of mangoes at point A. To be equally as happy, and let's assume, and I'll do it in different colors, maybe easier. Let's say this is point B up here. Remember, this point B means Alex would also be indifferent towards consuming this many fish, and then this many mangoes. So we notice that in order to be just as happy when Alex is getting less fish, he needs to be getting more mangoes, right? Intuitively, that makes sense. To be equally happy, if we give up some of one good, we should probably get more of another. Maybe there'll be in a few extreme cases where that might not be true. So the second property, the second of these 4 properties of indifference curves that we're going to discuss is that we prefer, I'm going to put them in quotes, higher indifference curves to lower ones. So right now we've kind of just seen one example of one indifference curve along in our Cartesian plane, right? So we have this Cartesian plane with the number of mangoes, M for mangoes, F for fish. We kind of drew this one indifference curve, what we labeled I1. In reality, there's there's an infinite number of these different indifference curves. And so let's say, for instance, there's one that's further away from the origin. And that's what I'm going to kind of higher. It's further away from the origin. Or we could have an indifference curve closer in. We'll call that I3. Well, let's draw out some points. So this is point A, point B, and point C. And so when we say we prefer higher indifference curves to lower ones, as a consumer, we want to be as far away on an indifference curve that's as far away from the origin as possible. So we're going to prefer any combination or any consumption bundle along I2, along this difference curve 2, to any combination or any consumption bundle on this I1. And we're going to prefer any consumption bundle on this I1 to any consumption bundle on I3. So we'd prefer to be at point B above point A, and point A above point C, and point B above point C. So the higher the indifference curve is, kind of the more total utility it's giving us. So this is what I mean by we want to be in the highest indifference curve possible. So maybe I should just write a little bit of that out. So we would prefer any consumption bundle on I2 to any consumption bundle, so any combination of goods on I1. And we would prefer any consumption bundle on I1 to any consumption bundle on I3. And so now maybe we're getting an idea of how we can represent the combination of goods that are going to maximize our total utility, right? We want to be on the indifference curve that's the farthest away from the origin we can get, the highest indifference curve possible. But what's constraining us is the budget constraint that we talked about originally. So eventually we're going to kind of put these two concepts together to graphically represent the optimal consumption bundle. But before we do that, we have to talk a bit of two more properties related to indifference curves. So the third property that we're going to look at is that indifference curves can't cross. Difference curves cannot cross. And so let's imagine they did and talk about how that would kind of mess with the logic of our indifference curves. So let's say we have two different indifference curves. Let's call that I1. Let's have a different color. And let's say this is indifference curve I4, and let's think of a couple points here. So let's call point A is where these two cross. Let's call this point B, and then let's call this point C. Okay, so what this is saying is we're indifferent between point A and point C because they're along the same indifference curve I1. So I1 is telling us we are indifferent between bundle A. We don't need a comma there, and bundle C, because they're all along the same indifference curve. And what I4 is telling us is we are indifferent between bundle A and bundle B. The problem here is that, if we were to apply kind of what we might call transitivity to this problem, we could say if we're indifferent between A and C, and we're indifferent between A and B, doesn't that mean we need to be indifferent towards B and C? But the problem here is that bundle C is giving us more of both of these goods than bundle B, right? If we mark out how much of each good we're getting in these bundles, in bundle C we're getting more of both goods. Well, it seems pretty crazy that we'd be indifferent towards two bundles where in one of the bundles we got more of both goods. But bundle C has more of both goods. Than bundle B. So it's creating this logical problem for us. So this is why they can't cross. And so then let's talk about the final property in a second, which is going to be that we usually see them as bow-shaped, these indifference curves. There's a reason I've been kind of drawing them as these bow-shaped. So the fourth and final property that we're going to be looking at is the fact that, in general, these indifference curves are going to be bow-shaped. Or just indifference curves. I don't know if we needed a "the" there. Difference curves will be bow-shaped. And so let's draw it out and talk about what that means in terms of the trade-off. So remember, this was the amount of mangoes, we had the number of fish. Remember, it's the quantities on these axes. Let's say we had an indifference curve, and this is an example of a bow shape. So this is what I mean. The slope is pretty large up here, and then the slope gets smaller and smaller as we increase whatever good is on the x-axis, so the number of fish here. And so to think about what that means about preferences, this assumption is saying certain things about the preferences of our consumers that we're looking at. And so let's think about kind of two different points and let's talk about point A here and point B here, then we'll talk about two different ones down here. And I'm trying to make it so the difference in the x-axis, the quantity in the x-axis between these two is the same. I don't know if I did a great job, but so what I mean by that is I'm trying to make it so let's imagine that this change is 1, just for the sake of it. And let's imagine this is the same distance. So what this bow-shaped is capturing is, if we wanted to increase our if we decreased our consumption of fish by 1, let's say, what the slope of this indifference curve here is capturing is if we're at point D and we had to get 1 less fish, how many more mangoes would we need to be just as happy? And let's say that the difference on this axis, for instance, is 2. Well, that's saying if we had to give up 1 fish, we need 2 more mangoes for our total utility to remain constant. Or if we wanted 1 more fish, we'd be willing to give up 2 mangoes to get that 1 fish to be just as happy. But notice that the slope is steeper up here. And let's say, if we want to go to the same numbers as the slides, that this was 6. And so now, if we're consuming less fish than over here, and we gave up 1 fish, we need 6 more mangoes to keep our total utility constant. Or if we were at point A and we wanted to consume 1 more fish, we'd be willing to give up 6 mangoes to consume that 1 more fish. So it's capturing the fact that the marginal utility of consumption is changing between these goods. And in particular, the slope is often called the marginal rate of substitution. So, marginal rate of substitution. And notice that the slope is falling, so the marginal rate of substitution is falling as we move down the indifference curve. So that's that fourth and final property. Kind of the slides talk about a special case when we have just a straight line for an indifference curve with perfect substitutes. But in general, we're going to kind of usually draw them these bow-shaped in our class.